Hi, everyone. Welcome to this week's Common Lisp Study Group. I'm your host, Ram Badam with Atlanta Functional Programming. My apologies to my live stream audience for starting a little later than usual. I was having some technical difficulties earlier, and I was spending some time prepping up for today's material. And anyway, better late than never. Today, we're going to continue our exploration of the Coalton library. Um, as of last week, I kind of gave you uh, what I understood of the brief whirlwind tour that README that's been provided to us. I was hoping today that we could spend some time looking at some of the built-in type classes that are in Colton. But before we do that, I felt that it would be more prudent for us to actually, tie up some loose ends from the last couple of weeks from our exploration. In particular, there was some weird errors that we were seeing with the do macro. If you recall, the do macro is actually a macro in Colton that essentially overrides the normal do that's available in Common Lisp so that the notation can act more like a progen and allow you to um, be able to run things sequence in Haskell in a Haskell-like fashion, particularly when dealing with monads, because the do macro or the do keyword in Haskell allows you to essentially run monadic transformations in sequence one after the other, and it makes sure that those sequence are strictly adhered to rather than allowing, as in most functional programming languages, since a lot of operations tend to be uh, taking in an input and returning an output, a standard normal pure function. The composition allows maybe one to potentially try some optimizations, like actually scheduling computations in a different manner, if if available, if the analysis allowed that to. Do actually allows you, with respect to monadic transformations, especially allows you to run things exactly in the sequence that you've defined them. So if you look at the example that we spent last week debugging, it was defining a function that actually took two arguments, grabbed them, and bound them to a um, local variables A and B. This notation here, again, if you recall last week, the left arrow notation specifically, um, unwraps a value from the um, monad that you passed in, and then sticks it into um, a variable for later use, as well as in this case, B's case, it will actually do the same thing. And we use these two values that we've unwrapped from the monads that are provided to add them together and return uh, uh, the result, ideally wrapped up in the monad that you passed in. So if we actually, if you recall, look at this function, I didn't actually load this particular project yet. I thought it would be easier just for us to play around with this example in the REPL. If we open this up in Colton user, we copy this expression, go into Colton user in our REPL and type in Colton top level, and we properly um, load um, this guy here. Let's go ahead and clean this up a little bit so that folks can actually. Huh? And if we look at this, this is our original function. If we do a type of on F, we'll see that what it gives us is what we saw last time. And you can also, for folks who want to know what are available, you could use the value database to actually grab this information, or not the type DB. Type DB is for all the available type classes. Um, Sorry, all the available types that are defined in here. So if we do type DB, if you recall, this is all the available types that are already defined in this location. And obviously, if we do instance DB here, we have all the instances that are defined. But we needed either print value DB or in this case we could just use simply type of. Okay, not kind of, type of. We see that this is a monad, and this is basically saying given to our type arguments A and B, where B is some numeric type and A is a monadic type, uh, create a function that takes in two monadic types of type B and return a monadic type of type B. Right, that's what this is. This here is saying. And you can see here when we click on it, the type checker is actually giving us, some of the generated values that it's actually getting. And in fact, if we try and partially specialize this, all right, which we could do so by doing top level define, let's call this TF, all right, and this is going to be nothing more than F being restricted on make list 1, 2, 3. Remember, we were actually trying to essentially add 1, 2, 3 to 4, 5, 6 last time. If we actually go and look at this and look at the type of TF, you'll see that it actually type checked and gave us what we expected, which is a function that takes in a list of integers and returns a list of integers because we provided a list of integers here, right? But if we go and try to complete the application, we pass in this function here. This is where things break down, and this is what we're going to be spending some time on today in debugging and see what's going on with some of the examples inside of the source code and the coalton source code. If we run this function, you can see that the problem that it's giving us is related to um, the fact that, and if I'm only guessing here, based on my understanding of this code, the pure function that you're seeing there, the pure is actually taking in um, uh, a value of type num, but it isn't a value of type, but it's not returning a value of type. It's not binding that value into something that is of type list monad, which is what we provided earlier. So I tried a couple things last time. If you recall, we tried maybe defining this guy here in our function, maybe as being the list itself. But by doing so, what we've essentially done is we changed the type signature now. All right. It didn't actually go and say, okay, what we're returning is going to be a return of type, um, of list. So there's something going on there that we need to actually kind of fix. So let's change this back here, and then let's return this back to what we have. Um, so one other thing is that I was going to look into, and this is in the type, not the type, the class DB. We can look at what monad is defining pure as. So pure is taking a B and it's returning. Okay, so monad is actually implementing applicative. We'll get into this when we have a bigger discussion on functors, applicatives, and monads, as well as monoids and semigroups, which are actually the prerequisites to actually get into all of the rest of those. But I'm just going to briefly mention where everything is kind of defined. And applicative, if we actually go and look at print instance DB, we could see that applicative is defined on list. So we need to see what pure um, does when we try to return, when we try to run um, when we try to just simply define a function that takes in an argument and it returns a list where we expect it to return a list of type A, right? So it will just make a single list. If we just tried this with a simple argument, we could probably see what um, what it's actually doing behind the scenes. So one experiment I was thinking of trying is defining a type G that, um, well, first we need to declare it. Declare um, G as being A, and see, how did I do that earlier? Um, Not integer, integer. I was hoping to actually provide you guys an example where we provide a numeric type. Well, let's see. Okay, we can always get this wrong and then check it out. So we take in a numeric A, and this is going to return an A, take an A, and a return, oh, and it will return a monad um, list of um, A. Okay, and then we define G of A X, and we say pure X. Now, this alone should give us a monadic function, but it says that it's invalid type, just like we had earlier. If coalton top level, let's define x's as being d of 5, and let's see what it throws. And it doesn't throw anything. So what is coalton of x's? It is a 5. So we've actually gone through and provided some sort of simple example that we can actually kind of work from. So let's see the next level of this. Um, let's do G prime. So we'll do define, we'll declare G prime, and this time we'll do num A, well, let's do num B, um, and, oh, shoot, I can't use comma here. See if I could do num B, dot, maybe num B dot, monad B, because these have to be lists. Cons with monad A equals, you take a B and you return A of B. Let's do this. Take an A of B and you return an A of B. This is not going to be an identity function. We're going to actually simplify this with just taking in one argument and returning one argument. All right. So I hope this is the correct way of actually specifying this notation. Otherwise, we're going to have to go look at some other examples. So we do g prime of x, and we're going to say g prime of x is going to give us a do notation where x prime is going to take out of, well, we'll say x's, and then we'll say x is one of the x's, and we're just going to do pure x. Let's see what happens. Malform type predicate. Maybe I can use an and in there. Let's look at the type predicates in our notation. So we have here, and look at maybe the example programs. And let's see this. Maybe this will have some stuff that we can leverage. So the type, okay, so I'm thinking maybe my type predicate needs to change in the following way. Wondering if I have to use logical and, sorry, I have to put unknown class type. Okay, interesting. Maybe I just need to specify here that it's list. Unable. Okay. Let's go up here and just unwrap this guy and see what happens. Oh wow. Okay, they did make it simpler. That's me being thinking that everything's a list here. All right, so let's see here. Type of g prime. Okay, so let's see if this works. G prime make list 1, 2, 3. This may not work as is in coalton user as invalid arguments, but if we generate what we did before, which is create fine y's as being g prime make list 1, 2, 3. This in a coalton expression. It's not a coalton expression. This analyze macro expansion. Okay, hold on 1 second. Let's see here. Let's get rid of this. Do this. Coalton top level.
Yeah, I think you misspelled top level last time.
Yeah. Do y's g prime make list 1, 2, 3. Okay, so what is this doing? The value monad. So this is giving us the opposite of what happened before. Okay, so let's go to our function here one more time. I'd like to just keep that there. And what I tried to do is I tried to grab the monad from X's should actually unwrap in the do notation. Um, maybe that's the problem. Maybe it's not unwrapping it correctly. Let's see. Let's do a let me just make sure if I can see. Unfortunately, I can't partially apply this function because this here should work. Kind of G prime. Actually, G prime is not a kind, it's a function. This may not. This is probably going to say that it's not concretized. Let's see. Maybe. No, it's not a prime. Okay. It's a function.
Hey, Rom,
Yeah, what's up?
on your definition, if you can pull that back up, yeah, there you go. So you say declare G prime, and then your constraints are that there's that numeric B is numeric and A is a monad, and then that given those constraints, you're going to have something that takes a monad and
And
then
returns a
also,
monad, right?
well, what you're returning, actually, what it says is you're returning a monad and a value, right?
Um, are you wait? You're
So it says
saying
like,
that this is a monad and a value?
right, and it's returning
The
a monad
pair?
and a value.
I don't believe so. So that's an
I think
interesting.
would it work that it just returns an A, right? Because an A is
Uh,
already a monad, right?
so if I did X like this, um,
I'm saying on your um, signature, right?
okay, I know what you're saying. Yeah. So the reason why this is written this way, okay,
Uh-huh.
is in uh coalton, and I could show you this. This is kind of the same way that this is defined in with our example that we saw earlier. It is it takes in it restricts the monad. Um, so the monad is still a parametric type. It's still a kind, right? It still
Mm-hmm.
requires you to provide some sort of concrete type in order for it to be realized and the type and the monad instance to be constructed.
Mm-hmm.
To actually display this in the Common Lisp REPL, what they've done is what they adopted is this notion that uh, a pair is going to represent the car of the pair is going to represent the monad, all right, that you're adhering to, and the coulter is going to be the value type. So what's inside the monad? So if
Okay.
you looked at the IO and string, it's going to
Yeah,
be
totally
IO space
understand.
string and
Yeah.
so forth. Um,
So this is a little different than Haskell then.
yes,
So okay, cool.
well, the function signatures are different than Haskell, but it should give you the same functionality. Like in Haskell, this would look like my guess is num a, b monad a, and it will return. Um,
It has to take an A, and it has to take that monad A, and then it has to take a B, and then it will return a monad A. Right?
yeah, and a b, and it'll return a monad a. Right, exactly.
Okay, so it's just notation. Okay, sorry.
Yeah, no, that's fine. The good question though. That's a that definitely for folks coming from the Haskell world or learning how the notation is in the Haskell world, this is a bit getting used to, you know. But that's also why I could say for certain that given that what I just wrote, it should appropriately check it and return a proper value, but I might be doing something wrong there. Um, Because ideally, what this should do is just the identity function. What I just wrote in this is essentially nothing more than it's going to take a list and return the list. It's going to iterate through the list and then put it as part of, you know, whatever we have. You know, um, if I did this, for example, I don't believe that's going to. Well, maybe. Let's see. The coalton G prime. Uh, Make list. Oh, well, hold on. Top level. Define y as being G prime. Make list. 3. And what is it going to complain about? You see, it's the definition that it's getting is different than what it's expecting. And I know if I change this to do, say, make list or pure x's, it's not going to work. db with an internal variable and c to cdc, right? So this doesn't work. And then of course, if I try to do a make list to a make list, this is going to be a completely different notation than what is provided by the signature. The signature is basically dictating this, right? Doing this. Oh, unclose parentheses, right? Sorry. This will only work if I could pass in a proper monad to maybe that's the problem, because in the readme, maybe I messed up in the readme. No, I didn't. This is exactly what they defined it in the whirlwind tour. So I did not screw that up. So if I do coalton top level, define y's as being d prime of make list. And what's interesting is if you look at this, f gives us this notation, which means the type inference is completely different. Um, okay, it's saying that num is not of type monad, but if we look at the other one that I just wrote, because I defined the signature, let's actually do this and not define the signature and see if we can get it to infer what those types are. X's, okay, and then pure X. See what the type is now of G prime. Huh. This actually may give us a different result. It doesn't put a restriction on B in this case because we don't have any options. Operators. So that actually makes sense. So if I do this, G prime make list 2, 3, that actually worked. That's good. And we can actually go now and look at, we do this and do coalton top level, and let's define y's as G prime make list 1, 2, 3, and type of y's. We see that it's appropriately a list integer. So far, if we just do not include addition, this is all starting to work, right? This is starting to, the type checker is doing what it's supposed to do with them and adhere to monads. But my guess is let's do an increment function. Define success uh, monad. All right. Sorry, let's call it successor for everything in the monad, and it takes x's. We define x to x's, and we do let y equal plus x and 1. This is basically the same idea, except we're not doing, um, what's it? We're not adding two lists, so it's not arbitrary addition. Okay. And now we're going to do pure y and see what happens. Okay. So what is our type again here on success monad? It knows now that we have to pass in an integer. All right. A list of some monad of integers. All right. So if we now do coalton top level, let's do fine g's. Well, we don't even have to do this. This should actually work in a coalton expression now. Success monad to make a list 1, 2, 3. It should actually give you 2, 3, 4. So if we're not doing monad to monad, this is all kind of working well. So why did something earlier, this one earlier did not, give us what we expected to? So maybe it is, might be the indentation. It's the only thing I could think of. AX, BX, do A to AX, B to BX, let C equal A plus B. Pure C. And if we do type of course, it's going to be now restricting it to saw earlier. And if we do coalton f of make list 1, 2, 3, make list 4, 5, 6, it's going to throw an exception. Sorry, a condition saying that the num is not of type mono. So maybe I could do this. Maybe I have to wrap this in some sort of and then specify list integer. Type error from this integer stuff. So if we look at the function signature that the function call is doing, the first argument is our numeric type. The second type argument is our monad type. But it looks like it is expecting the first argument to being our monad instance. So what happens behind the scenes is this, to give you guys some context, at least from my experiments the last week or so on this and trying to understand some of what it is. What the type checker does is it instantiates the type upon which you are trying to um, use, and it actually probably has this already available to you based on its inference model, what it determines to be the actual type of the underlying value. And what it does is it then delegates and well, not delegates, it actually sends this type information along with the data to the underlying generic function. Okay, so an f in this case. And what f does then is using some macro magic, it actually goes and determines, well, what type are we actually dealing with? It verifies some preconditions to make sure that all the types line up prior to actually running the computation. In this case, though, it looks like, and if the Colton developers are watching this, I encourage you to correct me if I'm wrong, so so I'm not, misrepresenting here. And by all means, come and join us to have this discussion because I'd love to have some more in-depth discussions on how this library works. But it looks like the monad instance is not getting constructed um, when f is evaluated because the actual macro expansion is giving something different. But I'm only speculating here. There might be a way of doing a macro expansion of what we're seeing here, but I have yet to determine that. We can try this. I don't believe this is generated as a macro, but it may be a macro. CL macro expand one F make, yeah, make a list 1, 2, 3, make a list 4, 5, 6. Yeah, this is not a macro. Um, Maybe if I do coalton here, does it generate? Um, Takes a list integers, and then passes it in. Okay. And what is ultimately being created in the code generator when it gets passed into F? That's the more important question. Um, Let me see if I can do a macro expand on our actual definition here, which will be pretty wicked if I can. Let's do this. Fine. Because this is a single macro, single expression, so this should work. I know I've defined this already multiple times, but I'm just trying to see if I can get more information from the REPL. Let's see. And of course, pure C. Okay, let's do this. So let's look at what it generated. Hmm, let's do this. I don't need this right now. We're going to start at the top, work our way through it. Okay, so eval when it loads up the global environment of all the type discussions that it figured out. And here it's setting the value type of our global environment F to being this function signature. This is all top level stuff too, actually. That's available already in the global environment structure if it hasn't been yet before it actually starts generating stuff. So we're just looking at a bunch of function signatures with some very nice here. Let's see here. This is all set F stuff still, setting up the environment. all the function signatures. Here. This is what I need. Okay. So once we define this, it's defining a new lexical variable f, and it creates our f with two additional arguments. These are the two arguments I was telling you about, the two types, ax and 0, and bx and b0, and aha, there's the problem. See right here, it's expecting the common Lisp type in the declarations to be of type monad in the first argument. But if you look at, this is what this is exactly what I was saying earlier. It is not actually, if you look at the signature, f is being passed in of type num integer here, which is wrong, at least based on my function signature, my reading of the code. Judd, do you see that?
Yeah, I was wondering, how can you then can you wrap that with a monad maker?
I have no idea. That's a very interesting question. We need to certainly, you know, this is a very interesting thing. Like the expansion of the code generation, though, this is clearly correct. What it's complaining about is correct, because what we're throwing is a number, and obviously the number is not of that type, right? So, um,
Yeah, so it needs a lift, right? Or return, whatever
but that's
Colton
what pure
called
is supposed to do.
it.
Pure
Well,
is
Q's at the end, right? So it wasn't it complaining that A is not a monad, right? Or was
it's
it
it's complaining that the inst so during so the way declare works is common Lisp declare. This is now, we're now in pure common Lisp land. We're not even
right?
talking about Haskell. All right, I'm
Okay.
sorry, not Haskell, sorry, Colton's type system. This is just pure vanilla common Lisp. All right,
Mm-hmm.
in vanilla common Lisp, it's basically doing an instance check to the first argument that was bound to the global symbol here, 885. All right.
Mm-hmm.
And if you look at the function signature, that global instance is bound to instance num integer, which is wrong, right?
Okay.
Now,
So
so
I mean,
basically the only way to fix this is to somehow swap the arguments. We can swap.
you
I
can
don't
do
know
that, right?
what.
You just do it. Just in Lisp, that's dead easy, right? You just
Well,
say,
I can do this manually. Like I could do this myself. Like basically if I do F here, okay, we have the full function signature. If I just simply say list here, which we have, okay, that's a symbol. Integer, which is also a symbol. Okay. And then if we just pass in the rest of this stuff, which is their way of defining um uh actually I don't even have to do that. Maybe I could just do this. This should generate what I expected it to. Wait, I mean, it looked like it ran. I have no idea why it. Function entry, arity1, arity1, arity1. Oh, I may have just I may have just skipped how it's handling the rest of this stuff. Let me see if I can do this in coalton itself and see what happens. Unknown binding monad list. Okay, you know what? Give me a second here. I'm gonna get those instance names that the function signature gave us in the debugger and then work from there. That's probably a little bit easier. Okay. Copy this guy out. Good. And quit. Paste. F. Now I have the actual instances themselves. Don't try this at home, folks. I'm not saying that this is valid usage. If this, I think I may have found an issue. That's all. Folks who are watching, wondering what I'm doing, I just may have found an issue with the code generation. That's what I want to do. Hold on. Again. Control W. So now the monoid instance is there. Monad instance is this. Crap. How am I supposed to? Track path instances directly. Okay, let me try something here. Do this, and let's grab this guy. And let me just see if I can actually get this to, inspect. Inspect. What is the way to find? Find the classes, but I don't think I could find a specific instance. Let me see if I could do what we saw earlier. Coalton library. Instance / monad. And unbound. Oh, sorry. 4. Instance / monad base list. CL find symbol. CL find symbol. Coalton library. Instance / monad list. Okay, there is a way to generate a symbol. I think it's CL make symbol. This one takes in a string, right? Yeah, it takes in a string. Instance / monad list. Okay. So what I have to do is I have to CL find symbol. CL make symbol. instance. I think this is what's going to give us what we need. Um, so it's not of type string. This needs to be a string as well. Oh, I did not realize that. Instance slash monad list. I forgot about that. In package, coalton cl find package designator coalton library. There we go. This is what I need to do. It's an internal, and if I find it, then what I could do is I could do cl symbol value, hoping that this is set to the instance. No, it's not. Dang it. Shoot. How the heck did this get passed in? It's probably doing a lookup of some sort. So basically, for folks who are just tuning in, wondering what I'm trying to do, um, these class instances for all the basic types that are built into Coalton are available in some internal dictionary in the Coalton implementation. And what's happening right now is what I have deduced, at least based on the evidence. It looks like if you have two arguments here, and based on the code generation, again, Colton library authors, if I'm making a mistake, please by all means correct me. But based on my understanding of, and I'm going to show you guys again what we did earlier, my macro expansion experiment earlier with this, we are passing in the in our original implementation, in our call, has the first argument to f, the instance num integer, and then the second argument are these two types are instance num integer and Lisp monad, and then we pass in the data. If you look at the actual macro expansion of the definition, see that in the define, in the defun, all right, we are expecting has the first argument this 897, and then we are expecting the second argument being the actual value type. Actually, we could probably fix this. Let me see if there's a way for me to look at the right. Again, not entirely sure if this is going to work, but it's always good to try and play around with the code generator that's provided. Let's see, where is that going to be defined? It's going to be in the type checker, I guess. Finds, parse types, predicates. See, the problem is unfortunately, I don't know at what point this definition kicks in the macro expansion. We could probably check to see. We could probably look up where define global lexical is defined as, and then fix this. Bottom line, just so folks can actually get an understanding of what I was talking about. Because these type declarations are specified for our two arguments in the order in which it's expecting it, monad being, of course, the first argument instance that is being passed in, and the numeric type for our example is going to be the second argument because we're using plus. When we pass in what I showed you earlier, num integer from the Coalton library, which again we're not actually passing it in. What's generated by the Coalton expression, the Coalton evaluator, is this. it is actually uh, doing a type check and says that it's failing the type check um, because the instance is obviously incorrect. The type instances don't match the type class that they're expecting. So and that's what's causing ultimately the condition to be thrown. Again, this is a code generation error that I'm sure that there are other ones, but if and I may end up I may actually just go ahead and report this because this looks like the example that they provided isn't what I expected it to do. So uh, again, I may be wrong here. I may end up getting, oh, this is why it's not working, but this is based on my reading of this. And because of this, the do syntax isn't actually doing what it's expecting to do in this particular case. I'm surprised that the other cases not actually didn't handle this, but it makes sense. In that other case, the one that I'm talking about is the G prime case that we defined, if you remember. Or G prime is defined as our, it takes an A and returns or even our successor monad, where we are adding an actual number to each things. Because we were actually um, providing only one argument and it was able to iterate through it. It didn't need to get any additional information. In fact, you could see in our G prime case, which is essentially an identity case, it did not provide any restrictions on B, so it could be anything. Whereas the other one, because we're using the plus operator and plus is restricted on numeric types, it got an additional type restriction. Same thing in this example here. Since we were in the successor monad, we've already passed in a concrete integer, 1, into the plus operation. It was able to deduce that, oh, we need to have some monad of integers, another monad of integers, and we should be just fine. In fact, because of that, I just got to go and double check this. Print type db, no, class db, sorry. And I don't know if they have a maybe type or a just type. Looks like they do not have a just or maybe. Looks like I would have to implement that, but I really have to go and look at how just or maybe types would work in this case and work through their type system. But I digress. What I wanted to show you guys is because of this successor monad being written this way, and we're saying all A has to be as a monad, you can take any monad that contains a integer and pass it into this function, it will automatically increment it. I can't seem to tell from these instances what other monads that I can probably play around with. Ooh, maybe vector? Let me see. Monoid is available and monad is available only on list and optional. Damn it. Wait, there's an optional. Okay, let's see this. Make optional. We actually used optional earlier before. It was the optional is going to be unwrap optional right here, optional integer. So we can't actually just generate an optional type. Doesn't look like it, at least. But we can pass in here we go. If we go back to our optional example, just 1 second here. And let's see here. Right. So if I do coalton foo2, I defined, oh, I'm in the wrong, let me go to our definition here. Now, if I do this, it says that it's unable to, oh, sorry. If I pass in foo2, this is going to go ahead and say sum4, but if I pass in nothing, it's going to give us none. So this is our optional type. If I then use this to actually go in, let's say 2, all right, which is going to give us an optional type with 2 plus 2, which is 4, because it's being parsed. And then if I wrap that and then call coalton on successor monad, which we defined earlier, this should actually say sum5. Oh, right. My apologies. I have to, since I'm not using exports, I have to actually specify them like this. Unknown binding coalton. Okay, so I'm going to have to define the successor monad in this area because the top of it's an unknown symbol. Not a big deal. We have defined it earlier in our history. One of the beautiful things about having history. I'm going to define it. And then let's see if this do what I expect it to do. Okay, so that means optional monads, there's something different than how we're expecting optionals to work. Okay. Interesting. It's kind of hoping that it would actually be able to figure that one out. Optional is basically the maybe type, by the way, folks. So I misspoke earlier. It looks like optional is available. It's just that it's, I think, in the type system has a parameter type. That's it. I'm wondering now if there's a make vector. Here is a make vector. All right, so let's see here. If I do coalton successor monad, well, first let's do coalton make vector one. Make vector needs a unit. Hold on 1 second. I have to go look now at type of a make vector to see what I have to pass in. Takes in a unit and returns a vector of A. Takes in a unit and returns a vector of A. Unit in let's see here. There is a function called unit. Okay, so let's see here. Coalton make vector and this is an empty vector here. Nice. All right. So how would I pass in a non-empty vector? If I do this, obviously this is going to, if I go back to here and I wrap this into success, oops, control X, sorry, control X, control 9. Oh, if I do success for monad on the empty one, obviously this is not going to do anything other than you can't find a vector from the monad. You're right, because it doesn't have it defined. So we're back to what we were talking about before. Like I can't really. So the only ones that I could talk through is lists and stateful computation. I would have to create a vector monad. All right. Since it's 9:20, I'm gonna stop here because we did find the source of our problems. So I can't say that we haven't actually, it wasn't all you know uh me just debugging. But I hope you guys can take away that this again, as I mentioned the last few episodes about Coalton, as I'm doing these experiments. Coalton is pre 1.0. A lot of these things will eventually get fixed. They are exercising, eating their own dog food, working through the problems, working through their issues. It will get fixed. It's just that it's not fixed yet. All right. It's and I encourage you guys to play around with it, find issues, report them, um, and hopefully those guys will love the fact that their library is being used and seeing a lot of issues, and will allow them to figure out a plan of attack. And if you guys are so inclined, um, pull requests, fix the problem and give a pull request. I think this library really needs some love from the community, not just these guys who've done a great job in actually building up the base of this system. Um, I'm hoping now that I kind of have a better understanding of what's going on, next time for us to cover um, the uh, some of the more fundamental algebras and talk about algebraic data types in general, then go and introduce you guys to the built-in type classes in Coalton, and introduce concepts that we're going to be covering in our Haskell study group as well. And that's the base algebras most people are familiar with when dealing with type design, and that is monoids, semigroups, functors, applicatives, monads. Although the order you should be learning about is semigroups, then monoids, then functors, then applicatives, and then monads. Because then you have a better understanding on how monads actually kind of work, and will design your types accordingly that way. So before I let you guys all go, a brief announcement. The next couple of weeks, we're going to take a brief hiatus and we will be back in February. Um, and hopefully we're going to continue our discussion on on Coalton, because I feel like the deep dive into Coalton and its available types classes will allow you guys to be able to do, a design where, a good portion of the system is written in Common Lisp and stuff that you want to have better type correctness. There you can actually just simply drop in Coalton, use it for whatever it needs, and then you know, work on your merry way. Um, and hopefully by the we can come up with some practical applications to show you guys in coding sessions during that time. So until February, I wish you all a happy new year, and I hope you guys have fun this New Year's Eve. Thanks for joining.
Okay, thanks, Ron.